Hi everyone, and welcome to this video on decision trees, where we're going to be talking about kind of the theory of decision trees and how they are constructed. We're going to start our discussion by looking at what entropy is, how we're defining entropy. This is one way of constructing decision trees, not the only way, but it's a good way of getting our basic understanding of how they work. And we're going to discuss entropy by really looking at very short episodes of me hacking away at writing stuff on paper. It's the best way I could come up with to explain this. It's not the most advanced high-tech way, but I'm hoping that using just kind of writing and casual conversation that I'll get across to you the important factors of how decision trees are constructed. So let's get started on this. Okay, I'd like to start our exploration of decision trees by looking at this simple example. This is a table showing whether someone mountain bikes or not based on various factors, whether the outlook was sunny or overcast or rainy, what the temperature was, what the humidity, whether it was windy or not. And the first system we're going to look at is called 0R, for zero rules. And that is, if we can't ask any question, if we're just to guess whether the person will mountain bike or not, what should we say? Should we say he mountain bikes or he doesn't mountain bike? And the simplest method to do this would just be to count how many no's there were and how many yeses there were. So there was 1, 2, 3, 4, 5 no's, and 1, 2, 3, 4, 5, 6, 7, 8, 9 yeses. So if we just had to guess without asking any rules, that's the 0, we would say yes, and we would be wrong 5 out of 14 times. So that's 0R. You can probably guess what 1R is. So 1R is we can ask one rule, one question. What is the outlook? And the person may say sunny, overcast, or rainy. What is the temperature? What is the humidity? Is it windy? And the question we have is, what's the best question to ask? Which one would give us the fewest errors? So let's figure that out. Let's say we're trying to do outlook. And the person says sunny. So if the person says sunny, well, let's just count how many there are first. 1, 2, 3, 4. 1, 2, 3, 4, 5 sunnies. So there's 5 sunnies. And here's a no. There's another no. That's 2 no's for sunny. 3 no's for sunny. And then a yes and another yes. So there's 3 no's and 2 yeses. So we'd probably say yes. And we would be wrong 2 out of those 5 times. Let's say he answers, it's overcast. There's 1, 2, 3, 4 overcasts. He mountain biked then. That was another yes. And 2 more. So there were 4 overcasts altogether, and we were wrong 0 of the times, because we'd say if it's overcast, he mountain biked. Finally, let's look at rainy. There's 1, 2, 3, 4, 5 rains. And here he mountain biked. That's 2 mountain bikes for rains. That's a no for rain. Another yes for rain. That's 3 yeses. And there was a no. So there's 3 yeses and 2 no's. So we'd say yes, he mountain biked, but we'd be wrong 2 out of 5 times. So here we were wrong 4 out of 14 times. And next we'd look at temperature and do the same thing. When it's hot, there's 1, 2, 3, 4 hots. He didn't. He mountain biked there. Oops, I missed one. He mountain biked then, and he mountain biked then. So that's 50-50. Twice he mountain biked and twice he didn't. Whatever we say, let's say he mountain biked, but we'd be wrong 2 out of 4 times. If it's mild, there's 1, 2, 3, 4, 5, 6 milds. There he did. 1. He didn't. 2. He did. That's 2 yeses, 3 yeses, 4 yeses, 4 yeses and 2 no's. We'd say he mountain biked and we'd be wrong 2 out of 6 times. Finally, cool. There's 1, 2, 3, 4 cools. He mountain biked, he didn't. He mountain biked, and he mountain biked. So there's 1 error there. This was going with Outlook, so these number errors were 5 out of 14 times. So if we were just look at these two, the best question so far is Outlook, and we'd proceed with the following. So that's basically 1R. We would just count how many errors we did and then select the question that was the best. Now let's see if we can kind of augment this to something we can really use with decision trees. And for that, I'm going to deviate from this mountain biking example just to talk about things in general. And before I even start, let's just review what binary numbers are, and especially this term bits or binary digits. And let's start with just base 10. So base 10, the first column is 10 to the 0. The next column is 10 to the 1. The next column is 10 to the 2. So we can keep on growing here. So 10 to the 0 is 1. 10 to the 1 is 10. 10 squared is 100, and 10 cubed is 1,000, and we'd keep going on like that in this 10 example. So if we have a number like 1952, that means we have 1 1,000th, or 1,000s, 9 100s, 5 10s, and 2 1s. It's kind of intuitive since we're so used to this number system. In binary, instead of 10 here, we have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and so on. So 2 to the 0 is a 1's column, 2 to the 1 is a 2's column. This is 2 squared, 4. This is 8, 2 times 2 times 2. And this is 16, and it goes on. So if we have a number like 10110, we have 1/16th, plus there's no 8s, plus 1 4, plus 1 2, and there's 0 there, so that would be 22. Just a quick review of what we mean by binary. So now let's give an example that we'll need. So suppose there's this house here, and let's say it's coronavirus time. That's where we are these days. And we want to see whether Anne's at home or not. We have this kind of person that's checking in a car, watching this house and relaying information back to some headquarters. And we want to know whether Anne's in the house or not. And what we want to know is how many bits do we need on average to transmit that message that Anne's in the house or not. And the answer is we need 1 bit, meaning if Anne's in the house, for example, we can say 0, and if Anne's not let's do the reverse. If Anne's not in the house, we'll say 0, and if Anne's in the house, it's 1. So as, let's say, hourly, this person reports back to headquarters, and it would just be a string, so we can say 1 1 1 1 0 0 1 1. So here at the first hour, Anne was in the house. Second hour, Anne was still in the house. Third hour, fourth hour, the fifth hour, Anne left. No one's in the house. Sixth, and so on. So on average, each message is 1 bit, right? That's a pretty simple example. Now suppose we have 2 people in this house, and we want to know whether they're both in the house, Anne's in the house, Sarah's in the house, or no one's in the house, and we need to transmit this information back. And the simplest method would just be to have kind of an Anne column and a Sarah column. So if neither were in the house, we would just say 0 0, If Ann was in the house, we'd say 0, 1. Sarah 0, 1, or 1, 0, sorry. 0, 1 for Sarah being in the house, and 1, 1, both are present. Right? So if we see a message like, I'll write that over here, like 1, 1, 0, 1, 0, 1, 1, 1, 1, 0. Let's hope this works out. So these are 2-bit messages. So I just kind of divide that. So the first hour, both were in the house. Then Sarah was in the house by herself, and Sarah was still in the house by herself. Then both were back, and then Ann was only in the house. So that's on average 2 bits. Each message took 2 binary digits. And now, if we had more information, the question is, could we do better? Could on average we reduce this to bits? And let's take a look at that. And now let's suppose we have more information about the situation. So here's my little state column. And let's say I know the probability of each state. So that's the added bit of information. So when the house is empty, that's true 50% of the time the house is empty. So if Ann is only in the house, that's, let's say, 1/8 of the time, so 1, 2, 5. If Sarah's in the house by herself, that's another 1/8, 1, 2, 5. And if both are in the house, that's 0.25. And now the question is, could we come up with a scheme of bits that would reduce our average bits we use per message from 2 bits down to something less than 2 bits? So that's the question. And the answer is yes. Let me show you that. So if no one's in the house, we'll just say 0. If both are in the house, I'll go 1, 0. And if Ann's in the house, we'll go 1, 1, 0. And if Sarah's in the house, we'll go 1, 1, 1. So what we want to make sure with our coding system is that it's unambiguous, meaning that if I had this empty be 0 and both were in the house as 0, 1, we wouldn't know if we had a string like this, whether the 0 here meant it was empty, was just the 1-bit 1, or it was the start of the 0, 1 message, right? So we want to unambiguously be able to divide up a string. This meets that. So let's see if that improves our situation if it's less than 2 bits. So here's the scoop. So 50% of the time, we're using 1 bit, plus 1/4 of the time, we're using 3 bits, plus another 1/4 of the time, we're using 3 bits, plus 25% of the time, we're using 2 bits. Now, if we did that multiplication and addition, we would get 1.75 bits on average. So we've reduced it. So on average, before, without knowing anything, we had 2 bits of information we needed per transmission, but now we only need 1.75. So we've reduced the number of bits we need on average. So this is kind of a key concept in what we're doing. Okay, so what we're doing is we're determining the average number of bits required to encode the likelihood of possible events. So let me give you a little bit of a quiz. Suppose I have a cat here, and this cat stays inside a house 100% of the time. So 100% of the time the cat's in the house, even when the cat needs vet care or the veterinarian comes to the house. So how many bits are required on average to encode the information that the cat's in the house? And I'm hoping you're thinking, well, it takes 0 bits. Right? The cat's always in the house. I don't have to tell you or encode any message about the cat being in the house. What about to encode the information of a coin toss? How many bits do you think are required? Well, I'm hoping you think takes 1 bit, right? So it's either 0 for heads and 1 for tails, or whatever the coding scheme is. What about to encode the information of a roll of an 8-sided die? How many bits there? And I'm hoping you think 3 bits, right? Because if there's a number 111, that's 1 4, 1 2, and 1 1. That's 7. And having all zeros there would be 0. So 0 to 7, that's 8 different numbers. We can do it in 3 bits. So what we're encoding here is, in some way, how surprised are we? How surprised are we that the cat's in the house, given that the cat's always in the house? We're not surprised at all. The surprise of me calling ahead and it is ahead, not that exciting. I mean, I have a 50% chance. The surprise encoding with an 8-sided die, it's a bit more, right? If I say I'm going to roll a 5 and I roll a 5, that's pretty exciting. If I have a 20-sided die and call a number, that's even more exciting. So it's kind of an element of surprise that we're encoding by all this. One final question. So here is the state of New Mexico. I'm kind of making these statistics up for New Mexico. But let's say 50% of the people in New Mexico speak English as a first language. That's the language they use in their house. And 25% speak Spanish. That's a little low based on considering what's true, but I'm just using this as an example. And 25 speak Navajo. That's extremely high. It's like 4%, I think, of the population speak Navajo. And then the question is, well, how many bits are required on average to encode this information? And this is a little bit trickier. So I could say 0 means English, 1 0 means Spanish, and 1 1 means Navajo. So 50% of the time I use 1 bit. 25% of the time I use 2 bits, and another 25 I use 2 bits. So on average I use 1.5 bits. So what we've been doing, again, is determining the average number of bits. And if we're just interested in the average number of bits and not the actual code itself, like if we're interested in knowing that it's 3.5 bits on average rather than 0 and 1 0 1 or whatever, if we're not interested in that but just knowing that average number of bits, we can use this formula called Shannon Entropy. And that formula is this. So we're arranging over all the different probabilities of the event. So that's the Shannon Entropy formula. So let's try it with a cat. The probability of a cat being in the house is 1. That's minus there. That's 0. So it takes 0 bits to encode that information. Let's do the coin toss. The probability of it being a head is 1/2 times log 2 of 1/2. Should put that big minus in it. And then the tail is 1/2. Okay, so this would be minus 0.5. Oops, these are minuses, sorry. So we get 0.5, negative 0.5 plus negative 0.5. So the number of bits are required, the number of bits required for a coin toss are 1. So the 8-sided die example, so we have negative again, And we have the probability of rolling any number is 1/8. So that's the probability of, oops, I shouldn't have done that. And there's 8 possibilities, right? So this is the possibility of rolling a 1, and then there's a 2, so there's 8 of them. So and log 2 of 1/8 is -3 times 8. So that's -375 times 8. It's negative. That's where that comes from. And that equals 3. Finally, let's look at the original example we were looking at. This one here, where we're investigating and looking who's in the house. Half of the time it's empty, quarter of the time both people are there, and 1/8 of the time Anne is there, and 1/8 of the time Sarah is there. So that probability is this. So we have, I'll just remember that we negate it at the very end. So we have 1/2 times log 2 of 1/2 plus, let's do the 1/4, 1/4 and we have 2 of those 1/8, so I'll just multiply this by 2. So we have 0.5 times -1 for this, plus 0.25 -2, plus 2 times 1.25 would be another 0.25 times -3. So let's do that. So we get 0.5 plus 0.75. These are all negatives. Oh, sorry. This is 0.5 again, sorry, plus 0.75. And that gives us 1.75 bits, which is what we came up with before. Cool. Sometimes when decision trees are discussed, instead of talking about entropy directly, we have a measure called info, which is directly transferable to entropy. And it works like this. So looking at this problem again, it would be info, and then we give how many occurrences of each state there were. So let's say there were 4 occurrences of it being empty, 2 where both were present, and then 1 each. And we might see that in the literature, and we simply translate it into probabilities. So there's 4, 5, 6, 7, 8 total possibilities here. So this 4 gets translated into 4/8 or 1/2. Right? This is 2/8 or 1/4, and these are both 1/8. And after we have that, we just use the standard Shannon probability. So sometimes you'll see this info occur. Now, the big question is, here's our original example of mountain biking. And the question is, can we use this idea of entropy, of Shannon entropy, to decide on what are the series of questions we should ask? So what question should we ask first? And based on the answer, what question should we ask next, to make kind of a decision tree, it's called. So a list of questions of how to answer. And the answer obviously is going to be yes, because that's why I've been talking about entropy for so long. And let's just, to start, do a simple one. Let's just look at the original entropy of this column here. So I'm just going to call it info. And we just add it up. So we have 1, 2, 3, 4, 5 no's. And 1, 2, 3, 4, 5, 6, 7, 8, 9 yeses. And so that's going to be the entropy, of 5 14s and 9 14. And that's minus 514. Oh, sorry, I'm spinning off the end here. And that equals, let me look it up. I'm not going to do the math here, but it's around 0.94. So the entropy of this initial problem is 0.94. And to explain the rest, I'm going to go use a computer rather than me doing handwriting. So that's it. I'll see you quickly as I fade out.